Okay, before we begin, do you have any questions about the course, about me, about the department? Okay, so if you have logged into OptoClass yesterday or today, you will see that there are already some information. This is the slide, the first meeting is these are the PDF documents that I used yesterday, and I will upload all the PDFs, or everything I write in OptoClass. I also made a recording of the screen and my sound. These are the videos over here, you can just listen to it, go over my notes. And there is now a prayer report, one of the first prayer reports. Well, this is just an exercise, let's say. I mean, I will not count it towards your final. If you want to give it a try, see how it works before the actual thing starts, you can just try this one. And when you click on this, okay, this is more or less what you should also see. So this is the start date. You can already upload your prayer reports. This is the due date. This is the deadline for the prayer report. This should be on Saturday, or no, this is on Sunday at noon. And the post date is when the grades will be announced. Well, I usually don't follow the post date, so you can just ignore this date. And you will only see your name, just a single line. And here you can just upload. Well, I will just upload one. So this is the title. You can just give it whatever title you want. And you can just type in the text here. Now, the first time you log in, the Turnitin will ask you to accept the agreement, etc. Just click OK or yes, whatever appears, and then you will be led to the screen. And then when you add the submission, okay, it's uploading. Okay, it might take some time, but it will just upload, and then it will tell you how much the similarity it has with other resources on the web. Okay, so it has uploaded successfully. So let's refresh it. Now it's trying to find the similarities, and when it's done, it will just let you how much the similarity is. So if you, for example, upload your prayer report early enough, and if you see that there are too much similarities, then you can just re-upload your document. You can update your document. Well, usually it takes several minutes. Okay, so this is what you should do when you want to upload your prayer report. Now, there's already one discussion. Okay, so let me restart it. Now, if you go to these discussion forums, you are probably already receiving emails from this discussion forum. There's already a discussion going on. There was a friend of you who asked a nice question, and there are certain discussions about that. Yes. Now, I will answer that question, by the way, today. We will discuss what's wrong with your solutions. Now, this is one diagram. Well, any question on the prayer report and up to class or the things that are uploaded there, your homeworks will also go there. So you will pick up your homework from up to class. Okay. Now, this is a nice diagram that I like. This for sketching what we are actually trying to do in physics as scientists, let's say. So we have the nature that's kind of everything that you observe around you, either with your senses or with the devices that you build. What we first do is we just kind of develop a numerical model for it. For example, we will be, I don't know, if you are studying, we will be studying the motion of objects. So you will be measuring the distances. That is what I mean by making a mathematical model. You just convert whatever you are studying into numbers. And then once you have the numbers, you can just play with those numbers using mathematics, using the tools that you will learn in your calculus courses this semester and the next semester. And in fact, if you already know that calculus was invented by a physicist, at least one of them was a physicist. So he just needed tools to manipulate this mathematical model of nature, and he invented them. And then once we have this mathematical expression, the step that is quite often missed is that we interpret our results. So what do those, okay, we find some numbers, but what do those numbers mean in terms of the nature? Our eventual aim is to try to understand nature starting from our observations about the nature. So this step is important, but unfortunately most of the time, at least in the exams, this is what is asked. So there is a model, this is given, and this is asked, but you miss all this, the interpretation of it in terms of the nature. What does it tell us about the nature itself? Now let's start with some modeling. The first example we will be discussing. Oh, before going that, let's discuss some units. We were discussing measurements. So, and we said that even when we are making measurement, in fact, we define, for example, the meter in terms of some wavelength of a particular light. So even there, we are comparing distances with some other distances in nature. That's what I mean by we want to understand nature in terms of nature. And units are always important. You should always pay attention to the units and also the definitions. Depending on the units and depending on the definitions you have, if you try to calculate cosine 0.5, you can get, for example, 0.88. Or if you calculate, in most of the calculators, this is what you would get. But what you want is cosine 0.5 is equal to 0.999961. So what's the difference between the two? What do you think might be the difference? Exactly. I mean, this is, at least in the discussion in the auto class, this is the angle that you are looking for. Now we have, usually you are probably accustomed to the measuring angles. Okay, we discussed measuring length, but we didn't discuss measuring angles. Okay, you are used to using degree. But most of the time we will not be using the degree. We will be using the radians. So what's the degree? What's the definition of a degree? Kind of. Well, not the length, but okay, this circle, we just define it to be 330 degrees, this angle. 360 degrees. This is our definition. Why 360? Well, I don't know. I mean, someone in the history liked this number. Well, it's a nice number because it is divisible by many things. So that's nice, 360. So they just decided to use 360 degrees. You can just invent your own units, and you might want to call this 400 degree, 400, at least it will not be degree, it will be something else. But these are what we call conventions. Now, conventions are just general agreements among the people. They don't really have to do anything with nature, they don't need to have any reason. The convention is that to define one full circle as 360 degrees. Well, rather than using these degrees, what we use is the radians. And the radians, this is how we define the radians. Take a circle again. This is an angle. Okay, we have this length of this arc over here. Let's call it L. And we have this radius over here. We have this R. And theta in radians is equal to, this is defined as L over R. This is the definition. Well, it's nice because most of the time when you are working with angles, okay, this is the arc length is something you would like to calculate quite often. Well, the arc length is nothing but the radius times the angle. If you want to use the degrees, and then the arc length will have a more complicated expression involving pi's and 180s, etc. So it just simplifies the calculation of the arc length. Again, this is just a definition, just a convention. A definition of a different unit. We will use this one. most calculators, most computers, by default, they use radians. And 0.5 degrees. Okay, so let's see, 0.5 radians is how many degrees? Well, let's see, this is 0.5 radians. Now, 360 degrees is just 2 pi radians. You see, if you, okay, this whole circle is 360 degrees. But if you take the whole circle, the length of the arc is 2 pi times r. If you divide by r, the full circle is 2 pi radians. So these two things are in fact the same, correspond to the same angle. So you are in a sense multiplying by 1. Now pi is something like 3. 3 times 2 is 60. This is something like, okay, let's cancel these one. This is something like 60. This is approximately 30 degrees, 0.5 radians. It's approximately 30 degrees. But I don't really care whether it is 35 or 25. So it's just an order of magnitude. It's just 30 degrees. And cosine of 30 degrees is, let's say, so this is what you actually want. When you write here cosine of 0.5, you are actually asking for cosine of 30 degrees. But that's not what you want. You want cosine of 0.5 degrees, which is very small in radians. And that gives you this number very close to 1. Now, another thing that you have to pay attention to, let's say quite often you write expressions like r over r plus 1.5. What's wrong with this? R is the radius of Earth, let's say. There's no units. You see, R should have some length unit. 1.5 doesn't have any units. So you cannot add a distance you cannot add a number to a distance. Is this length? Is this the speed? You always, even in your intermediate steps, you always have to keep the units. So the correct form of this expression will be 1.5 meters. Now, of course, you can think that most of the calculations you will be doing is just 1 or 2 lines. At most, it will take you 1 page. But imagine when you are doing actual research, your calculations will be like tens of pages, if not hundreds of pages. Whether you're a theoretician or an experimentalist, you will be taking hundreds of pages of notes. And you will have to go back to those notes and remember what you were doing like 1 year from now. And so whatever you write should be very clear to you. I mean, whatever you write, you will forget them in 1 year. So when you look at them back, you have to understand by just looking at it, reading it, what do you mean? Now, in this example, it's obvious that this was meter, and it was obvious that the distance that you find will be in terms of meters, but will you remember it 1 year from now? Probably not. So you should always keep the units. Now, whenever I give such suggestions to students, nobody cares. So I kind of enforce it. If you don't put the units, you will lose points in the exam. So just keep that in mind. And you do lose lots of points in the exams because you just forget the units. I think it is stupid to lose so many points because of the units, but if I don't force you, you don't do it. Okay, so any questions on these? Any questions on the measurements? So now we know how to measure distances. We have defined it in terms of a wavelength. We know how to measure the time as the time as, how did we define the time? From the cesium. We know how to measure the distance using the light the distance the light travels, and we had kind of defined, we didn't yet discuss how do we measure the mass, but we have defined the mass. Now when we study the Newton's law, we will be discussing how do we actually measure the mass. So we know all these measurements. Now let's first try to discuss the motion around us. Let's start with kinematics. Okay, I repeat, you will have access to all these notes that I write over here. So if you just want to copy these notes, that's fine. If I were you, I would just write the notes anyway, even if the notes will be available to me, because I basically sleep if I just listen. So just to keep me awake, I keep writing, but you don't have to write it. Now we want to describe the motion. What's motion? What's position? How do we describe position? Somebody else.
Something else.
Okay, with what something else?
I don't know, according to the table, maybe.
Okay, that's our reference point. So we chose a reference point. Now we will be interested in, to start with, as a simple example, just one-dimensional motion. So let's just imagine that, okay, here is the table, just pick up a point on the table. Okay, this point over here. Now let's describe the position of, what was your name? Umut. Okay, so this is the only direction we have. So how can we describe the position of Umut? No, we only have that direction and this direction. We don't have up or down or left or right. Okay, plus 3 meters. It doesn't have to be precise, let's say 3.2 meters plus minus 0.1 meters. Okay, so there are a few things. Every measurement has the error bars. Okay, in this course we will be most of the time using symbols, so we won't be bothering with the error bars too much, but just keep in mind that every measurement has the error bars. You have to know the error bars of your measurement. Otherwise it won't have any meaning. Okay, so what does this number mean? Okay, we said that the position of your friend, what was your name? Umut, the position of Umut is 3.2 plus minus 0.1 meters. Relative to that point, right? That's the reference point. So what does that mean? So if I tell you that, can you find Umut with this information? Why not? Which other information do you need? The direction.
Plus, but we don't know which side the plus is.
Okay, which side would you like the plus to be?
Obviously, on the side.
Why obviously?
Because we already defined this distance from the reference point, and the direction is given there, but
Okay, fine. So your friend is saying that that should be the plus sign. Well, not so obviously, by the way. It's just up to you. You could have just chosen that direction to be the minus direction. That's also fine. Now this plus 3.2 plus minus 1 meter is the position of Umut. So we had first chosen some reference point. Which point was the reference point? Well, arbitrary. It's up to you. You can choose whichever point you want. Then we said, okay, we measured the distance because we already know how to measure distances. We just we know the seconds from the oscillations of this atom, the radiation of the atom. We know the sec time, so we can measure the distance the light travels in that time in terms of meters. So we know this distance from our reference point. But of course that is not enough. Just imagine this line that since we are considering only one-dimensional motion, everything happens in this line. But there are 2 points that are at this distance from our reference point. One is in that direction, the other one is in the other direction. So we had to separate these 2 directions. Also, so just quite arbitrarily, we chose to call this direction the plus direction. So anything in that direction relative to my reference point, I would denote their position to be positive, and anything on the other direction, I would just denote to be negative. Again, it's just up to me. For example, what's your name? Sarkan. Sarkan, choose another reference point along this line. Right at the back? Okay. Okay, that's an alternative reference point. He has all the right to choose that. So what is the point of Umut? Umut, raise your hand. Okay, there is Umut. What's his position?
It's nearly at 0 because I choose Umut as my reference point.
Okay.
Plus and minus.
Let's say the position of Umut is this one. The position of Umut, let's denote it with a prime, is equal to 0 meters. This is valid. This is also, although you see the numbers are quite different, but they denote exactly the same position because there's a different reference point. Or you could have chosen exactly the same reference point, and you could have chosen this direction to be the positive, then Umut would be at the position minus 3.2 plus minus 0.1 meters. All of these numbers, although they are completely different, they are exactly the same position. Physical position, that's what I mean by physical interpretation. So these numbers do not really mean anything without this. You have to specify the reference point, you have to specify your positive and negative directions. With all these information, your reference point, the positive and negative direction, and this number, they will determine a position in nature, in real life. And all of these ones, so this is one measurement, this is another, this is one description of this position of Umut, this is another description, another valid description of Umut, and this is another, again, valid description of Umut. So they're all valid. Now let's look at displacement. So let's imagine that Umut just got up. He was bored in the class. So he got up and he went two rows back. So let's just, yes. For the time being, we are just fixing a point. We will come to the point when what happens when you can choose a reference point that's moving. We will come to that point. Now, first let's fix our reference point. Again, the point on the table is fine. You can just choose anything. So we had already determined that the initial point of Umut was 3.2 plus minus 0.1 meters. Now, sometimes just before the exam, students start to ask me some sample solutions. Here's a sample solution. This is what I also expect in the exam. If there are numbers, never forget the error bars, and never forget the units. And also in the exams, even when you are doing homework in your real life, just get used to, okay, in the tests, you have very little spacing where you can do your actual calculations. So you have to somehow make good use of that space. But in the exam, you will have as much paper as you like. So just don't draw arrows and point here and point there, write horizontally, vertically, just step by step. Okay, this is the initial position of Umut. And where would you like to move Umut? Now, along this direction. You are restricted to move along this direction. So your final position is, let's say, 5.3 plus minus 0.2 meters. So where is that point? Further back in that direction. Well, it is, let's say, 2 meters back. It's like four rows beyond Umut. How much did Umut move? What is the displacement of Umut? Now, when we mean the displacement of Umut, the displacement of an object, let's say this is how we show it. This triangle over here is what we call delta. Okay, when you graduate from the physics department, you will know almost all of the Greek alphabet. So this is your first lesson on the Greek alphabet. This is the capital delta, this symbol over here. And we usually use this delta to denote some small or large changes in a given quantity. So this just means the change in it. Now, the change in any quantity is always defined as the final value minus the initial value. This is the change in the position of Umut. What is that number? Two point one plus or minus 0.1 meters. Somebody else?
I can choose
0.2 plus minus 0.2 meters. Zero plus minus 0.5 meters. Plus minus 0.3 meters. Okay, other possibilities? Nobody is saying 0.4? That's the only one we missed. 0.4. Which one is the correct answer and why? Why? Well, that's the correct answer, but the why is also important. Why do you add the uncertainty?
So it's the maximum value.
Of what?
Subtract or we take the farthest final position and the least initial position, and we'll get 2.4.
Okay. 3.3 and, well, you see, your friend has a point. What is the maximum value of this possible displacement? Well, to get the maximum value, you get the maximum value of the final point, which is 5.3 plus 0.2, and the minimum value of the initial position, which is 3.2 minus 0.1, and that would just give you 2.1 plus 0.3. That is the maximum. To get the minimum value of delta x, you get the minimum of x final, you get the minus sign over here, the maximum of the initial point, you get the plus sign over here, and that would give you 2.1 minus 0.3. So this delta x would be 2.1 plus minus 0.3. At least within this course, that is the definition we will use of the uncertainties. That is not precisely true, by the way. There was a question? Yes. That is what the measurement tells me.
Yeah, that's...
Probably I use some other device to measure the distance, some device that is not precise enough. Now, these plus minus 1s or plus minus 2s are the things that the measuring device tells me. I mean, most measuring devices, if you make this actual measurement, you would probably use the same measuring device, and most probably both of the error bars will be the same. But just for the sake of an example, I just chose them to be different. Now there are, yes?
Will it still take the largest branch or maximum branch? Will it be close to truth?
Well, truth, the accuracy is a completely different problem. I mean, how are we sure that, well, we are assuming that this is accurate based on our definition. And we are also assuming that this measurement is accurate because we are using a particular definition of distances. Now, of course, when we are measuring, the actual distance would be somewhere in this range, but it doesn't have to be, let's say, the probability that it will be close to 3.3 will be small. I mean, it will probably be somewhere in between 3.1 and 3.3, but in between those two, not close to the edges, most probably. I mean, when you measure a distance, when you take a ruler, you can tell whether the distance is close to half a millimeter or close to a full millimeter. You can't tell it. You cannot be sure, but you can actually tell it. So the probability that this delta is actually close to 2.1 plus 0.3 will be in fact small. Not that large. I mean, if you are really unlucky in your measurement, you will measure xf to be at its maximum value and xi to be at its minimum value. Well, it will not happen. Most probably, if you are making a measurement and you are measuring larger distances, both of your measurements will be close to the larger distance, so the error will not be actually 0.3. Again, these are just definitions. So you have to make sure whenever you are looking at your measurement and the error bars, you have to make sure what do those error bars mean. Are you felt? Oh, yes. Okay. And then? Okay, let's do another example. Let's say the initial point is 0.2, final point is 2.1 plus minus 0.2. What is delta x? Is x final minus x initial, which is okay, 1 by 1 minus 0.9 plus minus 0.4. Somebody else? 1.1 plus minus 0.4. Minus 1. Okay. Somebody else? Both of these answers are wrong. Negative 1.1. Another wrong answer. Plus 1.1. Minus 0.4.
No,
Plus minus 0.4. The fourth wrong answer. Okay. Somebody has found one mistake. Okay. How did he get this plus? You always have to know why you are doing certain things. I mean, just because somebody tells you that you are wrong doesn't necessarily mean that you are wrong, by the way. Minus 0.9 meters. Anybody else? It is 1.1, by the way, this one. Always remember to add the distances, the units. Okay, any other questions on this one, on what do you mean by the distance? Okay, one thing that also frequently happens is, okay, your friend started from this point and then he went in the minus direction to 2.1 meters. So sometimes the students get confused and, okay, they use this definition but add a minus sign because it's moving in the minus direction. You don't add anything. And the definition is this one. This is the definition of the displacement of your friend. And it is always this one, whether x final or and x initial, they are larger or smaller than each other, it doesn't make any difference. This is how we define it. And when you tell somebody that the displacement is this much, this is what they will understand. This is what they should understand. You don't add minus signs if, I don't know, x final is larger than x initial or smaller than x initial. Okay, so let's assume that Umut was bored in his seat. He started at this position. He stood up, came to the front of the classroom, went out to buy some tea, and then came back and sat in his seat. What would have been his displacement? It's 0. This displacement just ignores what happens in between. The only important thing in calculating the displacement of somebody is the initial position and the final position. That is how we define it. Of course, he had, I don't know, walked like 100 meters or 200 meters going to the canteen and coming back, but his displacement would still be 0. Now, any questions on displacement? Okay. Now, we are not always interested in the displacement itself. I mean, for example, if you hear that somebody has traveled 1,000 kilometers, well, it would be really fast if he did it in 1 second, but it would be boring if he did it like in 10 years. So what we are interested in, the velocity, one concept, one quantity that we are interested in. We usually define it as the displacement per unit time. Okay, we will be defining 2 different velocities. One is the average velocity, which is nothing but the displacement divided by the time that the displacement took place. This is what we mean the average velocity. Now, we don't care what happened between the initial time and the final time, how much he moved, how much distance he covered, but only its displacement during this time. So this will be x final minus x initial divided by t final minus t initial. This is how we define it. Again, going on the example of Umut, he was bored, he went to the canteen and then came back, had a bottle of water and sat down, and then his displacement would be 0. If he did it in, let's say, 1 hour, 0 meters divided by 1 hour, his average velocity during that 1 hour would be just 0. Or we are looking at one-dimensional motion only. He just stood up, came down here, and went back. So and sat in his seat. Again, his average velocity will be 0. What about average speed? What's the difference between velocity and speed? Okay, exactly. Well, let's leave Umut alone for the time being. Okay, what's your name? Rahim. Okay, so Rahim is sitting over there. Let's change our reference point. So now we use this point over here as our reference point, and that is our one-dimensional motion, one dimension on which we can move. Now, Rahim, what's the position of Rahim? That is the positive and this is the negative. So we have chosen our reference point over here. We have chosen the positive and negative directions. So once they are fixed, we can write down the position of Rahim in a precise manner. So what's the position of Rahim? Okay. Plus, minus, what's your estimate of your error? So you are precise enough just by looking at this distance to measure his position by 10 centimeters? Okay. Okay, so this is the initial point of Rahim. Let's assume that he just came here to look at my tablet. So his final position is right over here. 0 meters. Let's say the initial time. Well, just like our reference point on this line, you can just choose we should choose some reference time. It can be anything that you like. And one way to fix the reference time to be, well, let's say, The moment that Rahim starts moving, that is RT equal to 0. That's how we define it. So this is 0 seconds. So how long would it take him to come here? 3 seconds. Okay, he's fast. Okay, so he just came here in 3 seconds. So what would be the average velocity? Hmm? Good point. What's the uncertainty in time? 0.2. Let's do it like this then. Okay, what's his velocity? More or less. I mean, we don't really care about exact values, at least during the lecture. Somebody else? I always see the same hands.
I think that it's minus 1.5 meters per second.
How do you get that?
I don't know the error measure.
Well, we are looking at approximate values, so how do you get that number?
I assume that because we didn't have a sign in the position, in the initial position, it was plus, so it was moving on the negative scale towards the reference point.
Okay, so what's delta x?
Delta x is minus 4.5 over 3 seconds. Minus 1.5 meters per second.
Do you agree with this calculation? What's wrong in this calculation? Okay, there's the meter missing over here. So it's 4.5 meters divided by 3 seconds. So this is the average velocity, minus 1.5 meters per second, approximately. Okay, the error we didn't estimate. We are not looking at the precise value. What's the average speed? It's 1.5 meters per second. The speed doesn't, well, in this case, in the one-dimensional case, the direction is given by this plus or minus sign. This is plus. And the velocity is minus. So this minus is just telling me that Rahim was moving in that direction, because that is our negative direction. That's the direction in which Rahim was moving. But the speed doesn't carry any direction information, so it's basically the absolute value of the velocity. Now, okay, so let's say Rahim started from that point, came up, looked at my tablet, and he wasn't so much impressed, so he went back to his seat. What is his second final position? So let's say this is T final is, how long did it take him to go back? So he was so tired coming up here. So 13.0 plus minus 0.5 seconds. Okay, so what's the average velocity from T initial up to T final? Why 0? He started from this point, he ended at the same point. So within error bars it is 0. So delta x is 0. So whatever the value of delta t is, since delta x is 0, it is 0 meters per second. What is the average velocity from T final to, or T final to T final? No. So what's this average velocity between the time he was here until the time he reached his seat? You see, the x final is 4.5 meters. X final is 0 meters. T final is 13 seconds, and T final is 3 seconds. 0.40. It is 4.5 meters is his displacement. He started from 0 and went up to 4.5 meters. So the displacement is the difference of these two numbers, and delta t is the difference of these two numbers, the last one minus the previous one. So it is 10 seconds. So it is 0.45 meters per second. You see, it's also positive. So that positive number just tells us that he was moving in the positive direction. I didn't put any negative when he was moving in the negative direction. The calculation automatically told me that the velocity was a negative number, and here I didn't put any negatives or positives anywhere. So again, the result of the calculation gave me the positive direction of his motion. Now, any questions up to this point? This one, yes. No, we measured it. We first decided on what should be t equal to 0. And we said that t equal to 0 should be the time at which Rahim started to move. So he was sitting in his chair. So we had our watch. So he walked down, we looked at our watch, and it was 3 seconds. He looked here, and then he went back, and when he sat down, we looked at our watch, and it was showing 13 seconds. So when he is here, that's our initial time, that is 3 seconds, and when he sat back, again, when we looked at our watch, that is his final time, it is 13 seconds. Now, in a given problem, you fix your reference points once. At the beginning, you determine which reference point you will use, what will be your positive or negative direction, what will be your t equal to 0 time, and once you fix them, you don't change them during the question. They are fixed. Because eventually you will be interpreting your results based on those initial choices that you made. Without knowing what your initial choices are, the final results will not have any meaning. So you have to know what your initial choices are, you have to keep them fixed.
How do you measure the measurement error in velocity given these measurement errors? Not on this screen, but we have point time, we have point 1, definitions of
Yeah.
etc.
So what is the error bar in V, right? What's the error bar in V? What's the uncertainty in V? That's what you're asking? Yeah. I mean, there are a few ways of doing that. The most conservative approach would be, what is the maximum value of V average? You get the maximum possible value of delta x and the minimum possible value of delta t, so you obtain the maximum value of the V average. You obtain one number. To obtain the minimum value of V average, what you do is you put the minimum number of delta x, the maximum possible value of delta t, and you get the lower value of V average. So that gives you the error bars on V average. In your Physics 107, in your lab course, you should be learning a different and somewhat easier way of estimating that. By the way, just to note, your labs will not start for a couple of weeks more. So you should go to, you will be receiving emails this week or the beginning of next week from your lab instructor telling you when you will be starting, what you should do, etc. Okay, so we have been receiving lots of questions about that. Keep patient, you will be informed. Now, any other questions on this? Now, okay, so our time is almost up. If you don't have any questions, let's give a 10-minute break and then see you after the break.